Okay, today we're going to start chapter 4, and we have been proceeding in an orderly manner. In chapter 2, we studied first order linear and other nonlinear differential equations. In chapter 3, we looked at second order equations of all kinds, and now we're going to talk about the rest, higher order equations of degree 3 or higher, of order 3 or higher, I should say. Today, we're just going to do some outlining of the themes of this unit, and then honestly, we'll go through all the lessons in this unit, but there's a lot that you really could do almost proceeding in a way that you would expect. You're going to see a lot of the same section titles on your assignment sheet. For example, I've got mine right here, in fact. Looks like we're going to do the method of undetermined coefficients. Looks like we're going to start with homogeneous equations, just like we did in chapter 3 with second order equations. Looks like we're going to look at the method of variation of parameters. So with all that, let's get into it. Now, I do have one more comment. I want to make sure that you haven't, it's actually not so important that you do this by today, but certainly by the time we get to the next two or three sections here, you're really going to need to know all that pre-calculus stuff that I asked you to review. I asked you to review a bunch of pre-calculus things, and it's going to become pretty important soon. You can see why. Because we're going to need all the things you know from pre-calculus about higher order equations. Long division and synthetic division. The rational root theorem, right? Ways of kind of getting at higher order polynomials. And also, de Moivre's theorem is going to play into this unit as well. So let's make sure we remember how to find the roots of numbers in the complex plane as well. So all those things are coming. So let's get into it, though, without much further ado. Let's see what we can generalize from chapter 3 with second order equations. This is basically it's the same, might be the exact same theorem that we looked at in chapter 3. Remember what we did is we typically put it in this kind of canonical form where we have the highest order term carry a coefficient of 1. And so you can see here, I'll give you a second to read this, but what we're going to do here is divide through by whatever the function coefficient is on the highest order derivative term there. I apologize for the notation. Each of those should be like, that's why I think you would interpret this, whether I told you to or not. But that y to the n, it's not y to the n, of course. That's the nth derivative. I apologize for the notation there. I should have parentheses around it or something. So we can divide through by that, and we're going to rename those functions just so there's no confusion. We've got p1 through pn as the coefficients on the corresponding terms of that order. And also notice that we've done a very subtle change. Capital G of x is not quite the same as little g of x. It's been divided by that a0 of x term as well. And so we have this exact same existence theorem that we had in the previous chapters. It's just the higher order analog. If all of those functions are continuous, then there's an existence and uniqueness theorem that guarantees that we will have a unique solution on that interval I, some interval for which it's continuous, right? And similarly, I won't go into it right now, but we'll see plenty of examples of them as we go forward in these sections. We can also do initial value problems. And of course, we kind of expect for a differential equation of order n that there be n initial conditions. Just think about when we were doing second order equations. We expected there to be two initial conditions and a value of the function y and then a value of its derivative specified. So, okay, we can also obviously generalize to a higher dimension the notion of the Wronskian. So let's actually compute that right now. It guarantees, I won't even read that. You can take a second to read it, but it guarantees the same thing, right? We're looking for linearly independent solutions, a fundamental set of solutions, all those notions that we talked about in the second, with second order equations. So let's take a second to think about how we might find the Wronskian of three functions. It, of course, amounts to taking some derivatives and then taking a 3 by 3 determinant So feel free to pause the video if you already have an idea of how you might do that. I think you should. We've had plenty of exposure to 3x3 matrices this year in various ways. In our multivariable calculus sequence, when we were studying those, we did a lot of cross products and things like that. So I think you should be able to do it, and I bet you'll get the right answer. So take a second to do that. And we're back. Okay, so you're going to take the Wronskian, of course, by loading in those three functions in the first row, and then their derivatives, and then their second derivatives are needed here as well. I'm going to expand using the top row just because that's what you're most familiar with, but as we proceed through this lesson, I may get a little more creative. You may remember that using kind of minors and cofactors to find the determinant of a matrix allows you to generalize this idea. Instead of going just across the top row, plus, minus, plus, and multiplying by those little 2x2 determinants, you can actually go across any row or any column if you respect those signs, that grid of signs. Okay, so we got x squared times the determinant of this, let me do some highlighting here, times the determinant of this guy right here, right? That's what appears here. Minus, remember that, x cubed times the determinant of these four elements here, that remaining matrix. So you get 24x cubed minus 8x cubed. And then plus x to the fourth times this determinant right here. And then all that remains is for us to simplify, and isn't that convenient? Everything has an x to the sixth. We get 6x squared, and then we can also maybe draw a conclusion about whether these form a fundamental set. So we'll say more about that on the next slide. Did you get 6x squared? So let's draw a conclusion about this as well. So here we've got three new functions. Feel free to, if you already know what this entails, again, pause the video and give it a try. Find the Wronskian. Doesn't say that, but of course that's what this means for us to do. So go ahead and, if you haven't already done so, try this. The first column makes this nice 1, 0, 0. That's 1 and its first and second derivative, and then sine 2x, note the use of the chain rule, and cosine of 2x and their first and second derivatives. Okay, so this is actually my first opportunity to maybe show you that we can expand across some other rows and columns. I'm going to maybe conceptualize this as being, as us going across let me grab a pen here. We're going to conceptualize this as going across down this column instead of across the top, like we sometimes have done, right? We can do that. And again, we have this kind of layout for the matrix. You have, and I'm trying to, at every step this year, I've been kind of trying to avoid teaching an entire linear algebra course, but you'll learn more about this in a linear algebra course. But we have these kind of these signs associated with each of the elements of the matrix. So if you expand across the top row, it's what you expect. You're going to have plus, minus, plus, like I know you guys are very used to. If you expand down this column, you'll actually have the same, plus, minus, plus. If you were to expand across the middle row, it'll be minus, plus, minus, and you can see how we might go from there. So I'm going to go down the first column. Do you see why? I really like all those zeros, because I've got, now it's really just one, this one right here, it ends up being, times the determinant of this matrix right here. And then the others will just be minus 0, this 0 right here, times the determinant of, well, who cares? And then plus 0 times the determinant of this matrix up here, but again, who cares? So now as we proceed, we take that determinant there. We kind of forget about the 1s and the 0s there. And look at that. Isn't that convenient? That ends up being just -8. And so then now it's time for us to draw the conclusion that, well, what is the conclusion? Since the Wronskian is non-zero, what can you conclude? Well, the same conclusion we made in the last chapter. The solutions here, all three of them, are linearly independent. So if you were to verify that these 4 different functions form a fundamental set of solutions for the differential equation, what would you have to do? Well, first of all, you would have to, don't forget this, you would have to do 2 things, really. You would need to, for each one of them, verify that they really are solutions to the differential equation. And then also, you would need to verify that they do in fact form a fundamental set. And if it's an order 4 equation, which this is, then we'll have the whole general solution if we have a set of 4 linearly independent functions. So here's the table I've created for you to help you organize your work. I think you can see what I'm asking you to do here. We're going to try and, because we need these functions, these 4 functions, although these are pretty easy ones to do. We need these 4 functions and all of their derivatives. Well, I guess really all we need is their second derivative and their fourth derivative. You can see in these 2 expressions. So the other parts of the table will be there too, though. Let's take a second to do this, and you already heard what the other step too. We're also going to need to check the Wronskian. So feel free to pause and take a few minutes to verify that all 4 of these are solutions and to compute the Wronskian. Okay, and when you're ready, let's take a look. So in the first column, I've got the derivatives of 1, which are, of course, 0, 0, 0, 0, the first, second, third, and fourth derivative. And so now I'm just going to double check that, is it true that the second derivative here, the differential equation demands that the fourth derivative plus the second derivative ends up being 0 right here. Is that going to be true? And yeah, and here we do get 0 when we add those 2 things together, of course. Now let's do t. The derivative of t is 1, and then after that we get zeros. And of course 0 plus 0 is 0. We can check those as well. Cosine t, here we go. How am I doing on my derivatives? Boy, whew, some heavy work here. And now you can verify again that this negative cosine t, we're looking at that row, those 2 rows there, the negative cosine t and the cosine t add up to 0. And then do the same thing with sine. Yay. Okay, so they all do work. Each one of them is a solution to this differential equation. Then we also have the Wronskian to check. Oh my goodness, Mr. Chase, I've never taken a 4x4 determinant before. Well, you're going to like this. Okay, so again, the presence of all these zeros is going to be nice. Again, with a 4x4 matrix, you're going to have associated with it this set of signs. You just alternate in this kind of diagonal checkerboard type grid. All right, so with that in mind, now we can, again, once you have that in mind, you can kind of, gives you permission to just go across any row or column. Well, instantly we all look at this column and say, let's give that a try, because that looks like fun. Because all I'm going to have to do is do 1 times the determinant of this matrix right here, this 3x3 right here. And then after that, it'll just be a bunch of zeros. Yeah. Okay, well now we've reduced this to a previously solved problem. You've got a 3x3 matrix, and there again, you've got that 1, 0, 0. I think you might be motivated, again, just like on the previous problem, to expand this going down the column. So we'll do that. It'll end up just being 1 times the determinant of this matrix, and the other things will be 0. And you maybe were intimidated by a 4x4 matrix determinant, but really in the end, because of all those zeros, we make pretty quick work of this, and we just get 1. And so therefore, since that's non-zero, we have verified not only are these all solutions, but we also form a fundamental set, and the Wronskian shows that. In continuing with the project of generalizing various theorems from the previous second order results that we have a result for Abel's theorem that gave us the Wronskian. So we're going to see a higher order version of this, and remarkably, it ends up being just exactly as simple as before. Notice the use of this term right here again, provided again that you have it in this kind of canonical form where you've divided through already by that highest order term coefficient function. You've like divided through by that. And we're using the kind of nomenclature that we were using earlier with P1. This turns out to be the only coefficient that matters in this formula. A proof of this fact can be found in Your book, if you'd like, you could take a look. I would say that it follows very similar logic to the proof that we gave for the second order equation, and so I just find that it's not illuminating enough to share with you during this, but it's fairly straightforward. You'll feel free to take a look. So in the end, that result is the same as what we've been doing. So let's now try this. Take a pause and do this. Remember what I said about the form of the equation that it needs to be in first. So pause the video if you haven't already and try that. And then I will do it here for you as well. Okay, so we're going to divide through by x. Did you remember to do that? And I've highlighted there in red again, just like up above, the kind of the key thing that we need. We need that 2 over x term. Everything else really can be discarded. Is that really true? Yeah, that's absolutely true. The only thing we need is that 2 to the x. So we apply the formula, and we integrate, and we get c over x squared. I skipped some steps there, but I think you've done that kind of integral so many times that I don't need to go through it. Obviously, we get a negative 2 ln x up in the exponent, and then we apply some exponent rules to help us resolve that expression. And that's it. Got a short lesson to kick us off here. We'll get more intense as we go forward. Thank you guys for listening, and other resources you can find in these links in the slide.